Today we are introducing the idea, or some of the basic ideas of, that is too small, of zero knowledge proofs. And I hate to inform you that we won't actually get to zero knowledge today because there's a lot of scaffolding that we need to build up before anything is going to make sense. What I will assume mathematically is essentially just some basic group theory knowledge, because all of the standard zero knowledge proofs, all of the classic examples, are proving results about some group relation. And we'll see that it's sort of the structure of groups really lends itself quite nicely to defining the kinds of proofs that we'll define. You can actually, as we'll get to in the long run, you can actually construct a zero knowledge proof for any NP language. But groups are structured in such a way that the protocols are really quite friendly and natural. Graphs too, which we'll look at in a future seminar. But today we'll stay mostly in the realm of groups. So, okay, we need to break down this concept as zero knowledge proof. We will explain what zero knowledge is supposed to mean. Intuitively, I will prove some result without revealing information beyond the fact that the result is true. And this is sort of, it's a related but different notion to what we normally think of as a mathematical proof. Okay, so what is a proof? Well, a proof, I have some statement that I will call X, and I will produce an artifact called a proof, and I will give you the proof, and you can verify whether the proof is true. Okay, so if V is some algorithm, I'm using that phrase deliberately vaguely. If V is some algorithm, you can run V on the statement and the proof, and V is going to output either 0 for it's a bogus proof or 1 for it's a legitimate proof. Okay, and when we think about mathematics, when we think about a formal proof calculus, our statements are some kind of syntactic construction, say in first order logic, and a proof is a series of logical sequence or something like this in your calculus, and the verifier is some deterministic algorithm that goes through each of the sequence, checks that they follow, and checks that the statement really is the one that's intended. Okay, so this is what we would call a non-interactive proof. Okay, most of the math papers, math textbooks, that's not the correct word, non-interactive proof. Most of math is done in a non-interactive setting, right? The prover writes down a proof, or maybe types it in some formal language like Agda or Lean, and then the verifier asynchronously sees the proof and goes, okay, I will check this. There's no interaction between the prover and verifier. It's simply sending the proof to the verifier. Now, on the other hand, what we're going to study in this series is mainly interactive proofs. Now, these are of quite a different character. Okay, so an interactive proof, the prover and the verifier are going to exchange messages during the process of generating the proof. And as a particular side effect, it's only an interactive proof is only convincing to the verifier that participated. Okay, so when the verifier is interacting with the prover to generate the proof, they are convinced that the proof is correct. Participate. Writing and talking is harder than it looks. I'm sure you both know this. I spelled it wrong. Okay, so an interactive proof, there's some kind of back and forth. The prover sends some information, the verifier responds with typically a challenge, right? The verifier goes, okay, well, if you really have a proof, you should be able to prove this particular aspect of it. And they interact like this, and typically only the verifier who participated is actually convinced that the proof is true. Okay, so this is clearly of quite a different character. but it is a proof system in sort of the formal logical sense, just as good as any other. And hopefully this will become clearer as we go. The link between formal logic and proof systems that we study in cryptography is quite a fascinating rabbit hole, and I really encourage you to go down it at your leisure. So let's look at an example, and this is one of the classics. What we really like to introduce is the colorblind friend. So the setup is you have two balls. One of them is green, and one of them is red. Now, your colorblind friend has red-green color blindness, and as far as they are concerned, these two balls are exactly the same. They cannot tell them apart. They are the same in every respect except the color, but because they're colorblind, they can't tell apart the colors, okay? And your friend looks at you and says, okay, you're telling me that these are two different balls. I don't believe you. You're going to have to prove to me that you really can. There really is some aspect of these balls that you can differentiate between that I cannot. And your friend says, okay, here's what I'm going to do. I'm going to take the balls and I'm going to hide them behind my back. Okay, so this is our verifier, the colorblind friend, and this is our prover, you. So your colorblind friend takes the balls, hides them behind their back, and they will choose one of the two balls and show it to you. And you go, okay, I've seen this ball. Then the colorblind friend is going to put it behind their back, shuffle them in some sense, choose one of the balls and show it to you. And then they ask, did I switch the balls? Now, because you can tell the two balls apart by color, you can always answer this question, right? You know, in this case, they showed you the green ball twice. So you say, no, you didn't switch the balls. If your colorblind friend had produced the red ball instead, well, you'd say, yes, you did switch the balls. So you know the answer, and you can always answer correctly. But if you didn't know the answer, if the balls really were identical, you, the prover, have a probability of at most 50%, right? 50% of answering correctly if the balls were the same color. Okay, well, 50% is not particularly convincing, right? 50% chances happen all the time. So let's repeat this a whole bunch of times. Repeat it, say, 128 times. What's the probability that you get every single question correct? Well, of course, it's 1 minus 2 to the minus 128, which is very, very small, right? So if you repeat this over and over again and you answer every single time correctly, your friend becomes more and more convinced that no, you really do know some secret information, right? The color of the balls, this is a secret because your friend doesn't know it, that you can use to tell them apart. Now in cryptography, we sort of say this is good enough, okay? We throw our hands up and say, well, most things that we want to do are impossible if there is no chance that someone could cheat. So we simply ask that the chance they can cheat is really, really small. This is the idea of negligible, which we saw in the last series of the seminar, which we'll revisit again today. Generally speaking, 2 to the minus 128. I just realized that I have written something that makes no sense. I can't believe Dan didn't call me out for this one. What I mean is the chance that you got all of them correct was 2 to the minus 128, which is way smaller than 1. Equivalently, your friend knows with probability 1 minus 2 to the minus 128 that you really can't tell them apart. That's what I meant to say. Okay.
Yeah, I zoned out because I knew what you were going to say.
Yeah, I understand completely. Okay, so this is a game, right, that two people are playing with each other, and we sort of have this convincing result that really the balls are different. And this game has two rather curious properties, okay? The first property is it only convinces your friend. Okay, your friend who participated in the protocol. Now, you might say, okay, well, your friend could film the whole process of the game and show it to someone else, right? But this is not a convincing proof, because it could be the case that you actually did it many more times and simply cut out the ones where you got it wrong, right? I mean, you have a 50-50 chance of guessing it right. You're going to get 128 correct guesses eventually. What's surprising is getting 128 correct guesses in a row, right? So it's only convincing to your friend. If they filmed it, they could show it to someone else and they would say, well, you could have just cut out the ones where they guessed incorrectly. So it's not convincing. We call this designated verifier.
You could also fail to ever permute the balls, which is, I guess, a failure you wouldn't make in this case. But if you imagine a more complicated example, there could be structure you don't probe or something, presumably.
Right, for sure. And so it's sort of a hidden detail of this game, right, is that your friend is supposed to toss a coin to decide whether or not they switch the balls, right? I didn't cover that in close detail, but it's supposed to be a random choice as to whether you switch the balls or not. Because if you never switch the ball and the verifier knows that, then of course it's a bogus proof, right? Like if you the verifier know, you the prover know what your friend the verifier is going to do. Well, it's not proving anything, right? Because you're just using their strategy against them. So that's a good point, and we'll revisit that as well. Okay, so it's a designated verifier proof, meaning it's only convincing to a specific verifier. This is a useful property in many contexts in crypto, particularly when we want to authenticate, we want to prove who we are. We can do a zero-knowledge protocol a zero-knowledge proof where I prove I am who I say I am, and you don't want the server that receives this proof to be able to show it to someone else to prove that they're you, right? So a designated verifier proof has this nice property where you can't just replay the proof to someone else that you get to someone else. Okay, and what's even more curious is your friend learns nothing. Except for the fact that the balls are different. So in particular, your friend doesn't learn... Sorry? What do you say, John?
I think you're about to answer my question. I should have just get my mouth shut. Please continue.
So your friend learns that the balls are different, but they don't learn which one was red and which one was green. And if you spend a while thinking about this, you should be able to convince yourself that even no matter what your friend, your colorblind friend, is doing, in other words, even if the verifier cheats, they can't figure out which one is red just by playing the game. All they learn is that the balls are different somehow. So this is the zero knowledge property. Now, obviously, I can't formalize it here because this is sort of a silly game that isn't mathematically defined. But this is quite surprising. The fact that this is possible is somehow quite unexpected, right? That you can really prove a fact, that you can prove that you know a secret without revealing any information other than the fact that you know the secret. This doesn't make any sense. But clearly in this case, this is what's going on, right? Your friend does not learn which one was red, which one was green, but they do learn that you know the difference somehow. Okay, so our goal today and next seminar will be to formalize the basic ideas of what the hell is going on here, because it's quite surprising that we can do this at all. And what we're going to focus on today is what exactly a proof of knowledge is. Okay. So the idea of the game is that you know some fact, you know that the balls are different, and you want to prove that you know this thing. What does it mean to know something? This is a question. Sorry to all my friends who study epistemology and ontology. This is a question that we're going to answer today. I can tell you with 100% certainty what knowing something means. Of course, I'm overstating this slightly, but for our context, there is actually a specific thing that knowing something means, and we will explore what that looks like. Okay, so let's get started with some formality, right? We want to treat this mathematically. We have to know what we're talking about. No pun intended. So our first basic definition is that of an effective relation, which is a terrible name, and I'm very sorry about this. So the idea, the light that we're casting this is we have a set of statements. So for example, in the colorblind friend game, the statement is the balls are different colors. And we have a set of witnesses, and a witness is some secret information that you can use to prove the statement. In this case, the witness would be ball 1 is red, ball 2 is green, for example. And then we define a relation between the two, okay? So every statement that is true comes with a witness that can prove that it's true. At least one witness, possibly many witnesses. And we want to do computation to this, so we introduce the notion of languages, language just being a set that a Turing machine, in this case, can recognize, and will require they're efficiently recognizable, meaning that the machine that recognizes them, or that there is a polynomial time machine. And the reason for this is because most tasks that we'll want to prove become trivial if you have unbounded time, right? You can just calculate the answer if you have unbounded time. So we're always working in this context of polynomial time or an efficient setting. So let's write this out. Okay, let R, X, W be efficiently recognizable languages. By which I mean that there exists a polynomial time Turing machine that decides membership of each set. And R is a relation between X and W. In other words, it's a subset of the Cartesian product. I have some extra dirt. Terribly sorry to my friends who don't like set theory, but I don't want to have to reinvent the wheel here. Okay, so we say X is the set of statements and W is the set of witnesses for each statement. And we'll see an example in a second to sort of put this in more concrete terms. Okay, so we say that an X is true if there's some witness for it. Okay, so in other words, there's a witness such that the relation between X and W is true. And if there's no witness, we say it's false. I should not equivocate here. What I really mean to say is that XW is in R. That's better. Okay. And when we have this set up, we call such an R an effective relation Okay, so we have a setting now where it makes sense to prove stuff, right? We have a statement X and a witness W. Now, a really simple proof for a statement would just be to publish the witness, right? But as we'll see, you can actually define something that is a proof without revealing the witness. And that's the whole point of zero-knowledge proofs. Okay, so we're not interested in the case where a proof is simply revealing the witness. Not very interesting. Okay, so let's do an example, sort of the archetypal example. This was one of the first instances of a zero-knowledge proof. In fact, the ECDSA algorithm, the sort of de facto standard signature algorithm, is essentially a zero-knowledge proof for this relation, except we didn't know what zero-knowledge proofs were at the time, so it's a bit weird, but it's essentially just this. So let's take a cyclic group. So GP is a cyclic group of order P. We're in crypto land, so P is always a prime number. And we want it to be generated by something called G.
Sorry, okay. I'm just noticing Matt was asking some questions in the chat earlier. Maybe you saw them or not.
Yes.
I think they may have been kind of resolved. It's fine, he says. Okay.
Yeah. Okay, very good.
I just wanted to flag that I am paying attention now, and I will pass on any questions.
Yeah, fantastic. Yeah, so I guess you could give your friend a concussion every time you guess wrong. This is this is sort of one of the perks of living in theoretical computer science, in that we disallow beating up the computer with a crowbar until it gives the answer you want.
But that's obviously not polynomial time. So.
That's obviously not polynomial time, exactly. Okay, so our first example is the discrete logarithm language. The discrete logarithm language is the relation d log with respect to a group and its generator, and we have a set of statements X, a set of witnesses W. The statements are group elements, and the witnesses are powers, such that G to the W equals X. Okay, so this relation is saying, well, it's a cyclic group, so every element X has a discrete logarithm W. In other words, G to the W equals X. And the language is saying, given a statement, which is a group element, I know the discrete logarithm W. This is believed to be hard in some groups. Obviously, we don't know whether P is equal to NP, so we don't have a proof that this is hard in any group, but it's widely believed to be hard in some groups. Z mod PZ is obviously not hard because discrete logarithm is just division. But there are groups in which this is believed to be hard. So it's thought to be hard, for example, in the group of quadratic residues in Z mod Q Z, multiplicative group of integers modulo Q. I'm being very careful with my notation here because, as an aside, cryptographers love to write ZP to mean integers modulo P. I'm trying not to do that here because a mathematician will complain that that's actually the p-adic numbers. So I have to think this through slightly carefully. Okay. The quadratic residues in this group, where Q is equal to 2p plus 1. So in other words, this is a group of prime order and therefore cyclic. So this is believed to be hard. We have no proof of this fact, but oh well. Other groups where this is hard is air quotes most elliptic curve groups. There's a lot of deep algebra involved in making that argument. As far as we can tell, most elliptic curves are good as long as they don't fall victim to a certain class of attacks. You can look into that in your own time. We're not doing that kind of thing, at least not today. Okay. So the intuitive idea here is that my power W, my witness W, which is a power in the group, is my private key, and G to the W is my public key, and I produce a signature, which is a proof of knowledge of the discrete logarithm with the message sort of mixed in there. And that's why signatures work that's why ECDSA signatures work in a nutshell. Okay, so now we want to define this interactive proof that I talked about before. So there are lots of ways, there are lots of theoretical or philosophical objections you could make here, but we're just following tradition. So a protocol is a pair, actually I'm not going to call this a definition. So a protocol is just a pair of Turing machines, a pair of probabilistic Turing machines. Okay, so the prover and verifier are being modeled as these probabilistic Turing machines. Sidebar, the prover doesn't always have to be probabilistic. There's sort of interesting theory behind that, but we'll make our life easier. Is a pair of probabilistic interactive Turing machines, which we write as PV. Okay, so you take a Turing machine. A probabilistic Turing machine has a tape of randomness, which you think of as essentially tossing a bunch of coins and putting that on a tape where it can extract randomness from it. Interactive is sort of a pain in the butt to define very carefully. See last seminar series for a painfully detailed exposition of that. But the basic idea is just the Turing machines have input and output tapes, and in some sense they can, the prover can write information to the input tape of the verifier and vice versa, so they can interact and communicate with each other in some sort of vague sense.
I will deny it was painful. It was not painful.
What was that, Dan?
It was not painful.
No, I wouldn't say it was painful, but it does get rather lengthy because it's really actually quite a subtle notion to understand. Okay, so we want to define a proof of knowledge, and the idea is going to be that you know something if the information that you give me contains that something. Okay, so if I can extract the information from you efficiently, then you know it. So in other words, if you can compute something efficiently, you know it. That's what knowing something means, okay? So the idea is for all possibly cheating provers, and when we talk about a possibly cheating prover, we'll put a little hat on it. So P means a prover that is following the protocol. P hat means a prover that looks like it is following the protocol, but might be doing something else internally. Okay, so all its interactions follow the protocol, but it might not be doing the same thing as P. So for all possibly cheating provers that make V accept, okay, so every prover that generates a legitimate looking proof, output accept. Accept is just a special symbol in the Turing machine language. Every prover that makes the output accept, you can extract. We can efficiently extract a witness from p hat. And if I just ended the sentence here, this wouldn't really make much sense, right? Because how is it supposed to be zero knowledge if we require that you can always extract the witness? Well, the trick is we allow the extractor to rewind p hat. In other words, to rig p hat's randomness and run it several times. This is sort of the first section where, this is the first moment where zero knowledge proof theory gets a bit wild. The idea is basically saying, okay, P knows a secret, and obviously P doesn't want to reveal the secret. But if we could force P to always toss the same, or say always get heads when it makes a coin toss, then it would inadvertently reveal its data, its witness. So we'll see how to formalize this in a second. But the idea is what we call rewinding access.
Well, the depth here has just gone several orders of magnitude.
Yes.
Can I? What's the relationship between V and the Turing machine that decides the relation R? At this point, is there any connection between those? I'm a bit lost between the bottom half of your second board and what came before it.
Mm-hmm. So I'm just defining. So here I'm just defining this setup. We have our language, which we're trying to prove stuff about. V is not deciding the language. V is, V sort of, okay, so very formally speaking, P and V each get a statement X on their initial tape. And P gets a witness W also on its initial tape. Now, very formally speaking, V needs to check that X is a real statement, right? So V should run the recognizer to check that it really is a legitimate statement. But then V does a bunch of other stuff interacting with P to see if P really knows a witness.
Mm-hmm. Okay, so far then in the definitions, it's not, for example, clear to us why we have to insist on polynomial time languages.
Yeah, so the reason for this is that it's very easy to sort of, if you don't insist on polynomial time languages, you end up with sort of trivial cases, okay? So, for example, in the discrete logarithm setting, discrete logarithm is NP, right? So if the verifier is allowed to run in unlimited time, if the verifier is allowed to run in unbounded time, then, well, of course it can extract a witness. It can just solve the discrete logarithm problem on its input. Exactly. So that's why we insist on polynomial time languages, because otherwise, well, there are no zero knowledge proofs for NP because you can just extract the witness always as an honest verifier.
Okay,
so
makes sense.
Yeah, it's because in cryptography we only care about statements. We only care about statements that we assume are hard somehow. And assuming P not equal to NP, the correct notion of hardness is polynomial time. We think. Again, I should really disclaim, crypto is a young field, zero knowledge proofs especially so. A lot of this is not set in stone in the way that a lot of math is. And if you look at some books, I'll provide references for further reading as well. If you look at some books, you might find some of this stuff defined a bit differently. Any other questions, Dan? I want to make sure this is as clear as possible.
Yeah, I think you're going to dig into more details, and I think I don't want to prematurely force you into them. So I think I'm following at the level you are wanting me to. Yeah.
Sure. Okay. So now
Matt asks, can you map it back to an example again? Like take us through this definition for the signature example.
Yep. We will see an example protocol in just a second, because I want to actually define this stuff properly. Yeah, we'll go through an example in a second. Okay, so I need a technical definition. This is not strictly required for the theory, but it makes the statements a lot less messy to define and prove. So this is another piece of sort of crypto canon. This is one of the few things that really is set in stone in crypto theory. So we define a function f from the naturals to the reals is negligible if for all powers in the natural numbers, the limit as n goes to infinity of n to the power of c times f of n equals 0. In other words, f of n vanishes faster than the reciprocal of any polynomial. Okay, so obviously if f is exponential, it satisfies this, but there are a lot of other functions between polynomial and exponential that satisfy this. The idea is just to have some notion of a function that is so small we can ignore it, okay? It's going to end up being a probability. If the attack probability is negligible, we say, well, it's so small that we can just ignore it. And this is how it appears in the formalism. Similarly, a random event as a function of a natural number. So I write x of n, and we say it occurs with overwhelming probability if the probability of x not happening, oh, my handwriting. The probability of x not happening is negligible in n. Okay, so it happens with overwhelming probability if the chance of it not happening is negligible. Decays faster than any power law, right, exactly. This is just it's a classic crypto thing. It sort of makes a lot of these definitions clearer. Okay, so now we're going to formally define what a proof of knowledge is. I'm going to define it as an interactive proof. Okay, so remember, a protocol was a pair of two Turing machines, a proof and a verifier. So a protocol PV is a proof of knowledge which we abbreviate as POK, for an effective relation R, if it is, first property, completeness. So completeness just says an honest prover can always prove a true statement. So for all pairs in the relation, if the honest prover runs on input XW, and the honest verifier runs on input X, the statement, then V outputs accept. Okay, very boring. It just says that if you give the prover a statement and its witness, and you give the verifier a statement, then the verifier always accepts. An honest prover can always prove a true statement. The other condition is soundness, which is arguing that a possibly cheating prover cannot prove that it knows something that it doesn't. And going back to this idea of extraction on the previous board, we're going to say that we need an efficient Turing machine that can always extract a witness from a possibly cheating prover if it can rig its randomness, and that's called a knowledge extractor. Okay, so the definition is that there exists a PPT, probabilistic polynomial time Turing machine, interactive Turing machine called EE, such that for every statement and every possibly cheating prover. Remember, p hat is a possibly cheating prover. So every possibly cheating prover that has a non-negligible probability of making v accept.
Could you put a little more detail into what possibly cheating means?
So yeah, we specify a protocol PV. P and V are specific fixed Turing machines. And they interact in some manner. They exchange messages according to a particular format. P hat is not necessarily equal to P, but it exchanges messages in such a way that it looks externally like it could be P, right? So in other words, it's following the interface, it's sending the messages of the correct format, but internally it might be doing something else. It might not. P is supposed to be calculating something based on the witness. P hat might be doing something completely different. It might be making up something that looks like a witness, for example. Does that make sense?
Yeah, okay. So this is like a version of observational equivalence, but for protocols.
Exactly.
Last time. Yeah.
Exactly, yeah. It looks the same. P hat looks the same as P from the outside, but internally it could be doing anything. So if P hat has a non-negligible chance of making the honest verifier V accept, in other words, output accept, we will abbreviate
Sorry,
this.
why call it possibly cheating then? What's cheating about it?
So it might be cheating in the sense that it might be producing a proof without knowing a witness. So in the honest protocol setting, the prover knows the witness and is outputting a proof. In the dishonest setting,
what here says it has to output a proof of anything.
Right. So what I mean is, sorry, when I say output a proof, what I mean is it convinces the verifier of a fact, right?
Yeah.
So in the possibly cheating setting, it doesn't necessarily have a witness, but it's still trying to convince the verifier that it has one.
Which it can do by definition, because the verifier can't possibly tell by any interaction that it doesn't know a witness. So how is it even possible to have a possibly cheating prover? I'm confused.
Yes. Maybe it will make sense when we do the example in just a second.
Okay.
The idea is essentially you prove that the only way the verifier accepts, the only way you can make the verifier accept is by either knowing the witness or getting very lucky and guessing the witness, which only happens with negligible probability.
Okay, so all right. Okay, I suppose your entire point is that there is no such thing as a genuine p hat, something like that. That's effectively what it means to be able to effectively extract a witness from p hat, isn't
it? Yeah. If you can extract the witness, then it must know the witness, so you can't cheat, except with very small probability.
Yeah. Okay. Gotcha. Cool.
And the very small probability is, as I said, you could just guess the witness, right? With the case of the discrete logarithm, you could just guess the discrete logarithm. It's possible. But of course, the chance of that happening is very, very small. Okay, so we say that if any p hat could make v accept a non-negligible amount of the time, then our extractor can interact with p hat.
The way you have these quantifiers written seems like the p hat could depend on x, but you don't mean that, do you?
Yeah, let me think about that for a hot second. Yeah, I should have written it the other way. You're correct. Yep. I'll fix that in the notes, which I will send you in a minute. So we allow rewinding. What we mean by this is the prover will choose some random values and then send messages based on these values. What E is allowed to do is make P go back a step, get a different input from the extractor, and do the same thing with the same randomness. So in other words, we're rigging the randomness And that's what rewinding means. If we're allowed to
Sorry,
rig the randomness, then the extractor can produce a witness.
I have another question. What's the
Yeah.
n here? I mean, the size of the group is fixed, right? So how
Yep.
can the length of inputs be increasing? What is it? How does...
The security parameter is in the length of X.
But the length of X is fixed because I have a fixed group.
Yeah, so what we mean is, in the context, hang on, I go back to the second board. In this context, n is equal to, it's equal to p. Right. So this relation is parameterized by the order of the group. So what we mean is that as the order gets bigger, the probability of cheating vanishes faster than any polynomial in the order of the group.
Wow, okay. So, so I'm supposed to view all of this as being parametric in P.
Yes,
which makes
parametric.
sense.
I guess I didn't explain this. Yeah, in theoretical cryptography, we have this bad habit of just saying, well, there's some security parameter and things grow in terms of this, and you're supposed to just go along with it. So every instance of this is implicitly parameterized by some quantity, in this case, the order of the group. And we say that as the order of the group gets large, the chance that you can cheat gets very, very small. Because obviously if the group is order 2, then it's not very interesting, right?
Mm-hmm.
And so the way that we get out of this is by implicitly parameterizing stuff.
Okay, so somehow, in some way, I don't care about P and V are sort of told when they start computing what P the X is from or something in particular.
They're given the parameters of the group and so on, yeah.
Yeah, okay, cool, thanks.
Okay, so our extractor can produce a witness. With overwhelming probability, we allow a small chance that the extractor fails. Okay, and E is called the knowledge extractor. That's not terribly important here. Okay, so our completeness condition is very straightforward, right? We have an interactive protocol, and we just ask that the honest prover and honest verifier can always prove the honest verifier will always accept a legitimate interaction with the honest prover. For soundness, we're saying we can always pull out a witness, except with very small probability, from something that makes the verifier accept. So there is no way to cheat except with very small probability. We with me so far?
This is so cool. Yeah, thanks.
And we're not, again, I'm just going to stress, we're not going to touch zero knowledge today just because it's super complicated. I'm going to go to the boards at the back to present an example, and we'll leave it there after that. Okay, so this example is what I alluded to before. It's the ECDSA signature example, and we call this Schnorr's protocol because Schnorr came up with it. This is the example that you are legally obligated to show people when they study zero knowledge proofs for the first time. This is the canonical example. And the way I'm going to do this is that we have P on the left, we have V on the right, and I'm going to step through the information they're given at the start and each step that they perform sort of diagrammatically. So at the start, we assume that they know P, G, such that the group generated by G is our group. I guess they know GP, they know the group, they know the order, they know the generator. They know some X in the group. The verifier has all of that information. The prover also has a witness such that G to the W equals x. Okay, so that's the initial setup. The first step is that P is going to choose a uniformly random K. Following crypto tradition, we put a $sign to say uniformly at random. This is meant to evoke the concept of tossing a coin, right? You toss a dollar coin, heads or tails, it's uniformly at random. That's the idea. So we choose some value K from the powers, and we set T to be G to the K, and we send T to the verifier. Okay, this is called the commitment. The prover is committing to a power K by sending T. And it's called a commitment because the prover can't if the prover just sent a random T, they wouldn't be able to figure out what K is efficiently. So they're committed to this value of K. And the verifier goes, okay, I'm going to choose a challenge uniformly at random. There's a small technicality here that you actually want the verifier to choose from a subset of the powers called the challenge space. And we'll explore that next seminar. So the verifier chooses a C called the challenge and sends it back to the prover. Oops, that's step 2. And step 3, the prover computes a response. So this R is set to K plus WC mod P. And they send R to the verifier. And do you see where this is going down? The verifier outputs accept if G to the power of R is equal to T times X to the power of C. Okay, so that's a protocol. What is this? What is this nonsense? Well, let's prove that this protocol is complete, and we'll at least convince ourselves that this makes sense. So we have R equals K plus WC mod P. So remember when we're proving I forgot to write completeness. So when we're proving completeness, we assume the prover and verifier are both honest. So G to the power of R is equal to, it's equal to G to the K plus WC, which is equal to G to the K times G to the W to the C, which is by definition T times X to the C. And that's completeness. Okay, so.
Sorry, Eleanor, can you just walk a little bit closer to that board so the camera follows you?
Yep. So we prove completeness. If everything is the way it's supposed to be, then okay, the verifier is going to accept. Easy. Any questions about that?
Nope.
Okay, now we want soundness. And we're going to, it turns out that this protocol is a very special case called a Sigma protocol, which makes life easier, and we'll explore this again in the future. So to argue soundness, we need to show that as long as the prover has a decent chance of making the verifier accept, then it really did know the value. So we assume, first of all, that 1 over the size of the challenge space is negligible in log P. So it's negligible in the number of digits of P, right? So as P gets really big, it's of size 2 to the n. So the 1 over the size of the challenge space vanishes quickly. So our extractor is going to fix randomness. And what I mean by this is that this means it's always going to pick the same commitment T. Okay, so the first step, it has to output some value. And by fixing the randomness, we ensure it always outputs the same value. And now the extractor is going to act as V to produce two transcripts. And the transcripts is just all the stuff that was exchanged in the protocol. Because P hat is externally behaving like P, we end up with transcripts T, C, R, and T, C prime, R prime. They're the same T in both cases because we fix the randomness. So P hat always has to output the same T no matter what. Okay. So now what we have to do is we want these to both be accepting. So if V does not accept both, so in other words, given C and R, given T, C, and R, we ask, would V accept? Given T, C prime, R prime, would V accept? As long if it doesn't accept in both cases, then change the randomness so we get a different T. And try again. So because P hat makes V accept with non-negligible probability, this is going to terminate in polynomial time with overwhelming probability. So it's not possible for us to get, it's all, except for a negligible probability, there's no way that we can fail to get this done in polynomial time. You can check the analysis on that if you really want to. Okay, so now we have these two accepting transcripts, and as you will see, we can just calculate the witness. We have G to the R minus R prime, which is just equal to G to the R divided by G to the R prime, which is equal to Tx to the C divided by Tx to the C prime. Because V accepted both, this must be the case. We just expand that out, we get G to the W times C minus C prime. So we know that W times C minus C prime is equal to R minus R prime mod P. P is prime. W is equal to R minus R prime over C minus C prime mod P. Sound. So what we see here is this pattern where you end up with two transcripts that have the same commitment. Okay, and this is an important special case that we'll explore in more detail next time. But this is a common strategy. If your proof follows that, if your zero knowledge proof, or I guess in this case, we haven't done zero knowledge, if your proof of knowledge follows this format, and you can show that given two transcripts with the same commitment, you can produce the witness, you are done. This suffices for soundness. Okay, good. So what we'll do next time is we'll see another example, and we'll sort of explore this special case in more detail, and then we'll move on to zero knowledge. Questions?
Oh, that was clear. Thank you very much.
Great.
Hey,
a possible, just for the record, okay. a possible, you might remember, I did say this was somehow related to signatures. The key is this challenge, right? If you look at this board, at the board with the protocol again, if the challenge contains the message that you want to sign, this becomes a signature for the message. That's the idea here. So you could imagine C is equal to the message that you're signing plus some random data, and this, therefore, the proof of knowledge becomes a signature for that because you must know the witness to produce a signature dependent on the message, so it's a signature. That's the link. If I'm trying to keep my secret secret, don't respond to 2 challenges generated from the same commit. Exactly. Yep. So that's why this first step, this commitment step, the commitment has to be chosen at random. Okay. If you ever use the same commitment twice, you are toast.
Yeah, but if the environment is malicious, then you're doomed. Give up. It has the ability to make you do whatever it wants.
Exactly. So the extractor or environment, you can sort of think of them the same way, Dan. If the extractor is allowed to make you answer again with the same commitment, then of course you are doomed. And that's how we produce this efficient extractor.
Can I ask a kind of high-level question, how you think about, I mean, clearly this example has the following format where there's a map, it's hard to invert. In this case, it's G, it's the exponential. And there's some algebraic structure on the domain of that map, which you can, I mean, if the prover kind of lives on that side and the verifier lives in the other side where the exponentials land. In this example, it's kind of, you can prove that you know the secret by doing operations on the domain, which if you didn't know it, you'd kind of have to keep going backwards and forwards along this map in order to compute that operation. Is that the kind of, I mean, are we exploiting somehow in the examples situations like that where it's possible? I mean, I guess I don't know how general the algebraic idea is that you operate in the, I mean, there's algebraic structure in the domain of the difficult to invert thing, and you can work there, and that's how you.
Yeah, this is where most of, I hesitate to say all, but certainly most real-world zero-knowledge proofs work somehow in this setting. So, for example, some of the really cutting-edge stuff is using polynomial commitments and elliptic curve pairings, and the idea is that the elliptic curve pairing is one way. And this is what you exploit. We pretty much always are going to be exploiting one-wayness in some sense, which is why we have the polynomial time stuff, right? We assume the existence of a one-way function, which assumes p not equal to np, and all the stuff that entails. I should say, if p equals np, we're not doomed. We just have to rejig the theory a bit to say, okay, x to the 10 is slow enough or something like that. But yeah, we're pretty much always going to be working in a situation where, in an algebraic sense, the prover can compute more stuff than the verifier because of the structure. Yeah, for sure.
Yeah, very cool. Thanks.
Matt asks, the rewinding thing is a theory tool. My browser will say, you want a second challenge response? No. Yeah, exactly. If your implementation of a zero-knowledge proof system allows rewinding, you are in big trouble. Yes. I really must stress this commitment does have to be completely random and never reused. Otherwise, you are toast. Exactly. Yes. I can't think off the top of my head of real-world examples, but I'm absolutely sure there have been cases where rewinding has occurred and has led to an attack, for sure. I guess ECDSA nonce reuse is an example of this, but ECDSA is really, because it's over an elliptic curve, things get very complicated, right? And it's very complicated, this exact scenarios in which it's safe and unsafe, but completely random, censored, never reused, yes. Does not, what do you mean, Matt? Birthday attacks are not relevant here because we're not looking for collisions, right? It really does have to be, right. Right, yeah, exactly. So completely random does not imply never reuse, but if you draw it from a big enough domain, in practice it does, right? If it's a 256-bit random number, the birthday paradox gets you down to 128 bits, which is considered secure. Yeah, we are sort of playing this game where we assume something that is unlikely enough will never happen, for sure. Yeah. This is sort of just the setting of crypto. If you're really paranoid, you could track every nonce you've ever used. But a lot of practical implementations don't bother, because it's really, unless you're the NSA, it's not a big deal, right?
Where there's several instances of gaps in time complexity that make this definition of knowledge work. I'm just curious where, I mean, it's possible they're kind of reduced down to the ones I'm in some sense familiar with from understanding public key crypto and signatures and so on, but I feel like there might be a new way that it's appearing in the definition of soundness, but I haven't quite processed it yet.
Yeah.
What's somehow essentially new?
Sorry, go on.
Sorry, I didn't hear that.
No, just go on.
Yeah, I can't really formulate it as a question, but I guess I'm asking for your intuition about where feels like there's some new idea here, and it has to do with a new occurrence of a gap in something. You're always pushing things apart with the time complexity in various ways. And what's the new idea here? Apart from you can mix, the old ideas with, logarithms and so on in groups. There's a lot of this is in some sense not new, but is this just a rehashing of the old idea? Or, it seems that the way this algebraic operation is happening in the group is maybe a little different than maybe more general than what I'm used to seeing in public key crypto, but maybe there's another new idea lurking somewhere in the definition of soundness.
So, yeah, I would say that the algebra is, I would not actually say that it's especially new. There's this idea that I present is really quite similar to how Algamal, for example, works. What's sort of interesting is the rabbit hole of zero knowledge proofs often leads you to new things that you want to assume are hard, like, for example, inverting elliptic curve pairings. The new idea in soundness to me is this concept of an extractor. Somehow this concept of rewinding access. This is the big new thing. And when you start thinking about what you want to be able to reduce the zero knowledge proof for, you're often led to new problems that you want to assume are hard. I would say maybe that's the link. Often you end up with wanting to assume something that is like a slight weakening or a slight generalization of a problem is hard, right? So you want to say, okay, not only is I'm just making some stuff up now. You might want to say, not only is the discrete logarithm hard to compute, but also if I add a number to it, it's still hard, something like that, right? This pops up a lot in the practice of zero knowledge proofs. You slightly extend the thing that you want to assume hard.
Yeah, that makes sense.
Okay, I'm going to leave it here, guys.
Yeah, thank you very much.